So last time we talked about acids and bases. And a reminder that pretty much an acid is something that has the ability to produce H plus ions in solution. And we're talking about really free H plus ions. Remember with acid-base chemistry, H plus and H3O plus are essentially the same. So you can use them interchangeably. H3O plus is the hydronium ion. It really represents the acidic part of the solution, just like H plus does as well. Bases are something that can create free hydroxide ions in solution. And that is really what makes a solution sort of acidic or basic, is really the ratio of the H plus to OH minus ions that are floating around really free in that solution. So if you have more of one or the other, it will tip it either acidic or basic. If you have really equal amounts of both, it will also be neutral. With that, we talked about the Bronsted-Lowry definition of acids and bases. And a Bronsted acid is a proton donor. So something that will give away an H plus. A Bronsted base is a proton acceptor. So that obviously is something that will accept an H plus. The result of sort of a Bronsted-Lowry definition of an acid and base is it does create sort of partners on opposite sides of the arrow. So when we take a acid and a base, we will end up with a conjugate acid and a conjugate base. And the relationship is the acid on one side is related to the conjugate base on the other, while the base on one side is related to the conjugate acid on the other side of the arrow. As we talked about, the only difference that there should be between an acid and its conjugate base or a base and its conjugate acid is really just the one proton that is basically transferred from the acid to the base. So it should only be one proton difference between those guys. The acid will have one less, the conjugate base will have one less proton than the acid, and the conjugate acid will have one more proton than the base in that particular case. We saw a relationship when water reacts, for example, with itself, it creates an equilibrium. And we could have an equilibrium constant, which is known as Kw. It's the ionization constant for water. That is the concentration of H plus times OH minus equals 1 times 10 to the minus 14. Again, here you could swap out H3O plus for that as well. That is really a constant number for our purposes, even though in reality, equilibrium constants like that number does change with temperature. But pretty much for our class and most chemistry classes, that's usually the value of Kw that you use. In most cases, if it happens to be a different temperature than 25 degrees, it actually would be a different value, but they probably would tell you, and that usually doesn't come across too much in our class and stuff like that. What we could use this is really, again, the H plus is really the acid part of the solution. And this is the base part of the solution. So it really is the same calculation regardless of what you're solving for. If you want the H plus concentration, you take 1 times 10 to the minus 14 and divide it by the OH minus concentration. Or if you want the OH minus concentration, you take 1 times 10 to the minus 14 and divide it by the H plus concentration. As we talked about last time, you definitely want to make sure that you use your exponent button in this chapter for sure. Otherwise, you are going to find yourself sort of off in terms of your values. We can compare those two concentrations. And if the H plus concentration is larger than the OH minus concentration, that means it's going to be an acidic solution. The acid part is bigger than the base part. If the OH minus concentration is larger than the H plus, it will be basic, more OH minus in solution. And if they do equal each other, they both will equal 1 times 10 to the minus 7, and they will have basically a neutral solution in that particular case. Any questions on that there? I think we finished up talking about the pH there and the pH scale. The pH scale runs from 0 to 7 to 14. Again, below 7 is acidic, above 7 is basic. And really, for lack of confusion, we, as we talked about, are going to go with 7 on the nose as being neutral. Again, anything above that or below that will either be slightly basic or slightly acidic. And that's really because the H plus and OH minus concentration would equal 1 times 10 to the minus 7, which should give you a pH of 7 really on the nose in that particular case. As you go from 7 to 14, you become more basic. And as you go from kind of 7 towards 0, more acidic. We could calculate the pH by taking minus the log of the H plus concentration. Again, you can also substitute out here H3O plus as well, same thing. Remember that depending on your calculator as to how you punch this in, if you have a display calculator, you're going to punch it in exactly the way it's written, negative log button. And then your number. If you have a non-display calculator, you can go opposite. You got to start with the number, you got to hit the log button, and then hit the negative button at that point. If you're not sure, again, which type of calculator you have, again, you know, you have to use hit log. And if it says log, you have a display calculator. And if it says error, you have a non-display calculator. So again, depending on which way you need to go, this formula and all the rest of them, pretty much that's how you need to put it in. Display calculator is always the way the formula is written. Non-display, you usually always have to start with the number, kind of work your way backwards when you punch it into the calculator. Any questions on that there? We also talked about significant figures and pH. Remember that the number of sig figs in your concentration value is the number of decimal places in your pH type value. So again, we had maybe something like this the other day, I think. And when we did our pH minus the log, we should end up with 5.00. This has 2 sig figs in our concentration. Once again, gives us 2 decimal places, not significant figures in your pH value, going that way. Any questions on that there? All right, so I think that's kind of where we left off. So I don't think we did this example here. So why don't we do this example? Let's calculate the pH for each of these solutions and determine, is it acidic, basic, or neutral? So these are 2 separate solutions. One has an H plus concentration, 2.1 times 10 to the minus 5. One has a hydroxide concentration of 5.9 times 10 to the minus 8. So take a few minutes there and see. Also, okay, let's take a look. So obviously we're looking for the pH. So pH equation seems like a good one. Minus the log of our H plus. So obviously pH means you need H plus, and that is what we have here. So we just need to go in. So pH equals minus the log 2.1 times 10 to the minus 5. Once again, if you have a display calculator, you're going to hit negative, you're going to hit the log. You go 2.1, your exponent button. You can go to negative button and 5. Yeah, it equals. If you have a non-display, you'll go 2.1, exponent button, negative button, and 5, then hit your log button, and then hit your negative button there. So whichever way you do it there, you should end up with 4.68 as our pH in this case. In this case, the concentration here has two significant figures, that means we end up not with two significant figures, but two decimal places here on our pH. Any questions on that there? This is acidic, basic, neutral. This one is acidic. It is obviously below 7 in this case. I might have mentioned it last time, but a reminder that there is just one answer to that question. Again, should either be acidic, basic, or neutral, not all three together and stuff like that. For the second one here, we once again are looking for the pH. And in this case, we are not given the H plus, we are given the OH minus. So it'd be a good idea. Perhaps one approach would be to solve for the H plus concentration by using our KW, which is 1 times 10 to the minus 14 divided by 5.9 times 10 to the minus 8. So 1 to the minus 14 divided by 5.9 to the minus 8. Going to give us 1.7 times 10 to the minus 7 molar, I believe. And if we put that then into our pH, minus the log of the answer, gives us a pH of 6.77 in this case, which is slightly acidic. Yeah, we'll go with. Any questions on that? Yes. Yeah, we're going to do that. And again, like I said, some people will say, hey, there's a range in between, 7 and stuff. So we don't have to try to figure out where the range kind of begins and ends. For our purposes in the lecture, just to make it pretty simple, if it's 7, it's neutral. If it's not, then it's going to be slightly acidic or basic. Unless it's like, like 7.0 something, then, you can still call it 7 and neutral. But anything slightly over that or less than that will go one way or the other, just to not have to try to remember where the gray area kind of may be. Now, if you maybe weren't paying attention and you thought you could perhaps go right in with this number here, and you calculated the pH by taking minus the log of 5.9 times 10 to the minus 8, and you got minus the log of 5.9 to the minus 8, gets you 7.23. You obviously did not calculate the pH, and that is because that is the OH minus, but you did calculate something that is what is known as the POH, which is a similar scale to pH, except that it measures the amount of OH minuses in the solution. And what you would have calculated there is actually, again, not the pH, but the POH. And that's not a bad thing, because there's a nice relationship that the pH plus the POH equals 14. Which means if you took the pH would equal 14 minus the POH, which would give you 14 minus 7.23, which would then get you back to the pH value that we had above. So it's not all bad. You're just like 2 slides ahead, I suppose, as to what you did there. But it actually is something that you can do there. As you can see, it actually is, as we'll talk about, a way where you don't have to use KW. It can make sometimes calculations a little bit shorter. So there are sometimes multiple ways that you could get to the answer, and that would be one of them there. But remember that if you have the OH, you get the POH. If you have the H plus, you could get the pH from that. This is also where people will oftentimes give the answer of it's acidic and basic at the same time. And that is because they will look at the pH and go, hey, it's like 6 point something, it's acidic. And then they'll look at the POH and go, hey, it's above 7, so it's basic, and say the same solution is acidic or basic. The pH scale and the POH, they run opposites of each other. So on the pH scale, 0 to 7 to 14, as we talked about, that is acidic. That is basic. On the POH is actually opposite of that, 0, 7, and 14. That is acidic. I'm sorry, that is basic down here as you go this way, and that is acidic. So if you have a low pH, you have a high POH, and vice versa. I would always recommend, though, when determining acidic, basic, or neutral, look at the pH scale and the pH number, because that's usually the scale that people have in their head. Most people do not have the pOH scale in their head because it's opposite. So always look at the pH to determine acidic, basic, or neutral, and do not give more than one answer for that. Any questions on that there? All right. So as we saw there, and as we will see, the pH scale is based on the log of 10. So every pH change of 1 is basically a power of 10 change. So 1 times 10 to the minus 3 is a pH of 3. 1 times 10 to the minus 4 is a pH of 4. By the way, if you have 1 times 10 to whatever, it's always going to be the exponent as the pH. As the amount of H plus increases, the pH goes down. Also remember that, as we talked about, the concentration of H plus and OH minus are tied to each other. So as one goes up, the other goes down, and vice versa here. As obviously the H plus goes down, the OH minus concentration will go up. And as the H plus concentration goes up, the pH goes down and the pH goes up as the H plus concentration decreases. So that is the relationship between those two guys. Are 3 things there that's important to remember. Now, there's a few different ways that we can measure pH. A very common one is to use a pH meter. This is a pH meter invented by a guy named Beckman there. And basically, it does a little chemical reaction there, but it measures the amount of free H plus ions that are basically floating around in there. And really, the real way it works is you calibrate it. So you say, it works off of voltage. So they go, hey, this voltage is like a pH of 7. This voltage is a pH of 4. This voltage is a pH of 10. Does like a little graph in the computer by itself. And then that knows that when it sticks it into another solution, it has this voltage. So that's like a pH of 4.3 or something. It's nice. It gives you a nice digital readout, obviously, of the pH. Another way that you can use or try to figure out the pH is to use indicator paper like this, kind of like swimming pool type paper and stuff like that. If you ever balance swimming pools, you take the little thing and try to measure the pH and all those kind of things. You'll do it in lab as well today. You'll basically dip the solution on the pH paper. There's usually some type of key there. You try to match up the colors and try to find the colors that match. And that will give you your pH of the solution. Also, times in the acid and bases, we do use litmus paper, and litmus paper does not tell you a pH or anything like that, but it will tell you whether or not the solution is acidic or basic. And typically, if your litmus paper stays or turns red, it's acidic. And if your litmus paper either stays or turns blue, it's basic. So we could sometimes just use litmus paper if we're not really interested in the pH of the solution, but just want to know, is it acidic or basic? You could dip a little bit of the solution onto the paper and it will turn either blue or red or stay blue or red, and it will kind of tell you whether or not it's acidic or basic in those cases. That is the pH scale and some common things. We have pure water at pH of 7. Sodium hydroxide, which is a strong base, obviously up there in base. Ammonia, a lot of cleaners, as we talked about, are bases. Vinegar, lemon juice, hydrochloric acid, or more acids. If you take water and measure the pH of it, will it be 7 in most cases? It will not. It'll probably be like in there-ish. It'll be acidic for the most part. And especially if it's water that's been hanging out for a while, because water will pick up some CO2 and make a little carbonic acid. And that carbonic acid will break apart a little bit and increase the amount of H plus that is basically in that solution, and it will lower the pH. So sometimes you're ever doing an experiment where you really are interested in pH and you want to make sure everything's sort of neutral before you start. Oftentimes people will boil the water. When they boil the water, it makes the CO2 less soluble, and it leaves and brings up the sort of pH more towards 7 of that water. In a lot of cases, like sometimes years ago, they don't do it very much, but like when we do the titration experiments, a lot of times people would, when they would make the solutions, they would boil the water and stuff like that to get the pH of the stuff to kind of start at neutral. So as we talked about a second ago, there are some similar scales to pH, which is like the pOH scale. And again, as I mentioned, it does run opposite of the pH scale. And the nice relationship there is that the pH plus the pOH equals 14. So if we add sort of all of our important equations up to this point, We have H plus and OH minus equals 1 times 10 to the minus 14, which is known as Kw. We obviously have our pH is equal to minus the log of the H plus concentration. There's our POH, and once again, our relationship between those two. So as I mentioned, it does give you a variety of ways that you could kind of solve these problems. In addition, let's add a couple of other sort of equations which are important as well. If you have the pH, you can actually get the H plus concentration directly from the pH value by taking the inverse log of the minus pH or negative pH. On most people's calculators, when you hit inverse log, that usually pops up a 10 and a caret. And then negative pH, or how a lot of people do scientific notation incorrectly, which is why you definitely do not want to do that for scientific notation in this chapter. On most people's calculators, again, top left corner there, the second button are the shift button, and the log button is what you want to hit there to get the inverse log. So that is, again, sort of how you hit it there. We could also do the same calculation there for POH. From the POH, you could get the OH minus concentration from it. And this is the exact same calculation. OH minus is equal to the inverse log of the negative POH. And again, a 10 and a caret negative POH is usually what will pop up on your screen. Same rules apply for this formula as well, depending on display or non-display calculator. If you have a display calculator, you're going to type it in just like it's written. If you have a non-display, you kind of have to go the opposite way. You got to start with the number and then hit the inverse log, and then you'll be good in that case. So you got to go that way with it. Any questions on any of those there? All right. So as you can see, you can really avoid KW in some cases, or you can use KW. It will get you the same answer depending on the path that you choose. So why don't we try one for each of these? Why don't we calculate everything, make sure our calculators work? So let's calculate the OH minus concentration. Let's do the pH, the POH, and is it acidic, basic, or neutral? And then for this second one, let's do the same thing. Let's do the H plus concentration. Let's do the pH, the POH, and is it acidic, basic? Okay, let's take a look, see how you're doing. So we're really looking to solve for everything, make sure we know how to punch it in. So at this point, you really have two options. Since you have the H plus concentration and we're looking for everything, you could use KW to get the OH minus concentration if you like. We could also go directly and get the pH. So that's what I'm going to do first. I'm going to choose to go and get the pH here first, which was the original question. So we're just going to put it into our pH equation of 3.6 times 10 to the minus 9. When we do that, minus the log 3.6 exponent button minus 9, going to give us a pH of 8.44 in this case. At this point, I do have the pH, so I can get the POH from here, or again, I could still use KW to get the H plus. So that's what I'm going to do. I'm going to use that the pH plus the POH equals 14. That means that the POH here would be 14 minus our pH, and that would give us 14 minus 8.44, and that would get us 556 as our POH. Any question on those two? At this point, once again, you could still use KW to get to the OH minus, but I'm going to do the other calculation here. Now that I have the POH, I am going to get the OH minus from it by taking the inverse log of the minus POH. So on your calculator, that's going to be a 10, a caret, and negative 5.56. So once again, to punch that guy in, second or shift button, log button, and negative button, 5.56. basically. And if I do that, somewhere on my calculator here, there we go. Looks like we will get something like about 2.8 times 10 to the 1, 2, 3, 4, 5, 6 minus 6. This does need molarity as it is a concentration. Again, here I am going from 2 decimal places to 2 significant figures. So again, going backwards, we want to follow the same rules to do that. That would mean that this is acidic, basic, or neutral. This is going to be basic, as we do want to look at the pH value that's above 7. So this would be basic. Once again, not more than one answer for that question. Any questions for yourself on that? Once again, it shows you as well, if you chose to use KW up front, you could have got to the OH minus concentration the same way. The OH minus concentration would equal 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 9. And again, that should get you up there as well. So that's, again, all should get you is really the same place. Any questions on any of those numbers there? Okay. The second one here, we're looking for really the same stuff, except we're looking for H plus in this case. pH, POH, and acidic, basic, or neutral in this particular case here. So let us see. In this case, I'm going to get the POH in this case, because I do have the OH given to me, minus the log of 9.2 times 10 to the minus 2. That will give me a POH of, looks like 1.04. And since I have the POH, I could easily get the pH by just taking 14 minus the POH. And that gives me 14 minus 1.04. Going to give me a 1296 in this case. At this point, to get to the H plus, I'm going to use that same formula there. pH, going to take it to get to my H plus. The inverse log of the negative pH, and again, a 10 and a caret, negative 12.96. And it looks like 1.1 times 10 to the minus 13. Once again, we do need molarity there for our concentration. In this case, we would want to look at the pH once again, and the pH value here is above 7, which means it is basic. Any questions on any of those steps there? Clearly, you need to be able to calculate those things. Yes. Any questions? Okay. All right. So let's try a couple more here. Just make sure. The pH of a solution is 5.67. Calculate the POH and also calculate the H plus and OH minus. Okay, let's take a look. So again, a couple of places you can start with. Since we have the pH, we can easily get the POH. That will be 14 minus the pH. That'll give us 14 minus 5.67. And that's going to give us 8.33 as our POH. Again, at this point, we could get the H plus concentration by taking the inverse log of the negative pH. So punching that in, 10 and a caret, negative 5.67. Make sure, again, you use your negative button and not your subtract button. Otherwise, you might be in some trouble. And you'll end up with 2.1 to the minus 6 here. Once again, that should have a molarity as it is a concentration. At this point, you could use KW and take 1 times 10 to the minus 14 and divide it by that number, and that would get you your OH minus, or you could do the same calculation for this guy, which would be the OH minus is equal to the inverse log of the negative POH, negative 8.33. Now, if you do that there, you will get about 4.7 to the minus 9. And once again, that would be molarity. Now, on some of these, you may be getting a slightly different number, depending if you're not in scientific notation, and frankly, your calculator runs out of digits, and maybe you just get like a 5 or something at the end, or a 4 or something at the end, and that sometimes will happen if your calculator is not in scientific notation. Your just runs out of units, runs out of numbers, basically, and rounds the last numbers. So that sometimes will happen when you're doing some of these guys here. Yeah. No, so again, in this case, we would look at the pH value. That was 5.67. It has 2 decimal places, which means when we take it back to concentration, the concentration should have 2 significant figures. So it does depend really on the pH value or the POH value as to what you just should end up with. But this guy should end up in this case with 2 significant figures. Again, not decimal places in this case, yeah. And again, every number that's before the times 10 part of scientific notation is significant, right? So that's how we get to 2 significant figures there. Other questions on that? Okay, so let's just do this one, the question it asked. So what is the H plus concentration? 3.1. So like we've done before here, this is the one where we're just going to go directly into our equation to calculate it. Again, want to make sure you do make it negative there. Otherwise, obviously, you will be off. And we will end up with negative 3.14. Looks like 7.2 to the minus 4 here. Once again, molarity would be our unit in most cases. Once again here, 3.14, 2 decimal places there on our pH value, giving us 2 significant figures on our concentration. So again, depending on which way you're going, you want to sort of follow the rules backwards or forwards there. Any questions on that one there? All right. Obviously, if you were not in scientific notation, you probably had something like 0.00074 on your calculator, which obviously is the same number. Yeah. You don't have to write it in scientific notation if you don't want to. Just make sure you have the right number of sig figs. Yeah. All right, one more here to finish this one out here. POH is 5.67. What is the OH? Okay, so once again here, your only option, because the only number you're given is the POH, is to turn that into your OH minus concentration by doing the inverse log of the minus POH. So that's going to give us a 10 to the negative 5.67. That'll get us, looks like 2.1 to the minus 6. Looks like a winner. In this case here. Any question on that there? So there is really no way to use KW off of this problem, right? Because you don't have the H plus concentration or OH minus concentration. So you are sort of forced to calculate it using the inverse log method. Any questions on how to calculate H plus, OH minus, pH, POH? Again, you do need to be able to do this, and people oftentimes get confused on to which equation to use for which. So again, if you're doing any type of pH or POH calculation, those are your minus the logs that you want to kind of use. If you're trying to find H plus or OH minus from a pH or POH, then that is your inverse log of the negative, whatever it may be. So those are the two major ways that you want to kind of use those formulas. Any questions on that? Okay, up until this point, pretty much all of our sort of problems have been maybe generic, like, hey, the H plus concentration is this, which is the acid, or the OH minus concentration is this, which is the base part. You can be given a problem that involves a strong acid or a strong base, and out to calculate the pH of it. We talked about some strong acids, and just a quick of that list: hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, nitric acid, sulfuric acid. Those are all pretty much strong acids. Remember, for the most part, strong bases are going to be your group 1 and 2 that have hydroxide in it, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So those are your strong bases. Pretty much, if you remember this list, which is a good one to remember, anything outside of that, you could probably safely assume is going to be a weak acid in most cases. So what does that mean? If you do have something like HCl, which is a strong acid, when it goes for a swim, because it's really a strong electrolyte, it will 100% break apart into its ions, which means in solution, you have none of this guy still together, but you do have 100% of basically these guys in the solution. So really, in a solution of HCl, you basically have all these guys floating around like so. To calculate the pH, we do need minus the log of the H plus concentration. So really, the important thing for figuring out the pH of a strong acid is to figure out the H plus concentration. And really what we need is the molarity of the whole thing. If you remember, we talked about molarity. It kind of works like stoichiometry. It's a 1-to-1 relationship, which means the molarity of the H plus would actually be the same number, right? If it was a 1-to-2 relationship, you would have to multiply it by 2, or 1-to-3, whatever it may be. And that's how we would then have the molarity of the H plus, which means we could then go into our pH equation. We could also do this for something that's a strong base, like sodium hydroxide. When it's in solution, it's going to 100% break apart into sodium and hydroxide. Remember, though, that in this particular case, if we know the molarity of our sodium hydroxide, it is in this case a 1-to-1 relationship between the hydroxide, which means we actually would know the hydroxide concentration. That would not give us the pH, but that would give us the POH, right? We would be able to solve for the POH, which is good because then we could get the pH by taking 14 minus the POH. So you could also figure out the pH of a strong base solution by figuring out what the correct hydroxide concentration is, calculate the hydroxide concentration and the POH, and then get to the pH by subtracting 14. Any questions on any of that there? Now, if we had something like 0.1 molar HCl, that would mean that our HCl here would break apart into H plus and Cl minus. And since this guy is 0.1 molar, it is a 1-to-1 relationship between that and the H plus, which is really what we need. That means that the H plus concentration would also be 0.1 molar. And that's really all we need there to go into our pH equation of minus the log of 0.1. And that should give us a pH of 1 here. And in this case, it would be 1.00. That is an acidic pH, which makes sense since that's an acid. So we should have obviously an acidic pH. Any questions on that? Also, the answer to part 2 of the experiment today, solution number 1 should be that answer. Any questions on that there? All right, so why don't you try one here or two? So calculate the pH of a 0.025 molar perchloric acid. I want you also calculate the pH of a 0.025 molar calcium hydroxide solution. We'll assume that is a strong base, and we'll assume obviously this is a strong acid. to see what you come up with for each of those. Okay, let's take a look. See, so this is a strong acid. So we know that means it's a strong electrolyte, which means it will break apart in solution into H plus, which is what all acids do. And in this case, perchlorate, as the other guy, is really the H plus that we're interested in to calculate the pH. So if this guy is 0.025 molar, it is a 1-to-1 relationship between those two, which means this would be also 1.1 times 0.025 molar, which means the concentration of the H plus will be the same. That is good because we could just go into our pH now, minus the log of 0.025, and that will get us, looks like 1.60 as our pH. That is acidic and that's an acid, so that is good. Again, if you got like a pH of 13, not so good, probably something went wrong along the way. Any questions on that? This is going to be a strong base, I know, because I see hydroxide there, so that's probably a good hint. When this guy breaks apart, we're going to get a calcium ion, and we're actually going to get 2 hydroxide ions. So it's going to break off for a minute. It's actually the OH minus that's important here to allow us to get to the POH. So if this guy's concentration is 0.025 molar, it is a 1-to-2 relationship here, which means the proper concentration of hydroxide would be 2 times 0.025 molar, going to get us 0.05 molar as our hydroxide concentration. That again is going to allow us to calculate the POH in this case. The POH would be minus the log of 0.05. So minus the log of 0.05 gets us a 1.30. If you by some chance thought that was the pH, it should not make sense because that's a 1.3, which would be a acidic pH if you thought that would be. And this is obviously minus 1.3, which is our POH, and that gets us a 1270 as our pH, and that does make sense as this is obviously a base, so that is a basic pH in this case. Any questions on that? I would say probably in most cases, your strong acid, strong base, the H plus or OH minus concentration will be the same as the whole thing. But there is an occasion like here that it may be, you may have to adjust it by multiplying by 2. But in a lot of cases, it will be a 1-to-1. You could probably safely assume in our class here that if you have an acid or base formula given to you and you're asked to calculate the pH, that it is strong, because to calculate the pH of a weak acid, it's a much longer calculation, yes, and you do it in 1B. So you could probably safely assume that it's probably going to be strong acid or base if they actually do give you a formula in this class. Outside of this class, as you continue on, it could be a weak acid or weak base. Any questions on that there? All right, the last thing we're going to talk about in this chapter is our good friends buffers and a buffered solution. So a buffer is really a solution that can resist changes in pH even when you add more acid or base to it. There is a very common misconception about a buffer that a buffer is a neutral solution. And a buffer is not necessarily a neutral solution. You could have a buffer that is neutral, just like you could actually have a buffer at any pH you like. So you could have an acidic buffer, a basic buffer, you could have a neutral buffer. You could literally make a buffer at any pH that you want to make it at. When you make the buffer, what it means is, for example, if I make a buffer at a pH of 5 and I add acid to it, it will stay around a pH of 5 if I made a good buffer. It may go down a little bit, maybe it goes down to 4.9-ish or something like that, but it will not go from like 5 all the way down to a pH of 1 when I add acid to it if it is a correctly made buffer. If I start with a buffer at a pH 5 and I add base to it, the pH will go up maybe a little bit, maybe it goes up to 5.1 or something like that, but it will not go from like a pH of 5 all the way to like a pH of 13 if I made a good buffer. So again, it's able to really keep the pH constant. And the reason it's able to do that is actually what a buffer is made out of. And a buffer could be made out of one of two combinations: a weak acid and the salt of its conjugate base. Or it could be a weak base and the salt of its conjugate acid. What are those two things? Those two things are your Bronsted-Lowry definition. These two things basically are a difference of 1H plus. These two guys, right? That's how one way you could recognize, could this thing be a buffer, is if those two things that you want to make it out of are basically related to each other by 1H plus, just like the Bronsted-Lowry acid conjugate base pairs. You cannot make a buffer out of a strong acid or a strong base. That is a big no for a buffer. So you cannot make a buffer out of those two things. And the reason why that is a strong acid is a strong electrolyte, which means it will 100%, for example, if we had HCl in solution, it will break apart into H plus and Cl minus. This is my acid, this is my conjugate base, which means in solution, the only thing I have floating around is H plus and Cl minus. I have none of these in solution, which means the only thing I really have in solution is a base, which is not really good for how a buffer works. Same thing if you took something like sodium hydroxide, breaks apart into sodium ion and hydroxide. This is a base. This is sort of its conjugate acid, if you will. And really in solution, if you put sodium hydroxide in solution, you have sodium and hydroxide. You have really a acid, conjugate acid there. You have no base because there is no sodium hydroxide units still together. The reason why a buffer works is because it's able to keep in solution both an acid part of the buffer and the base part of the buffer. They're actually in there together. So when we say a buffer is made up of these two things, both of those guys are in the solution to begin with, together, floating around. And they're able to do that because they are a weak electrolyte. So for example, a couple of common buffers is like HF, hydrofluoric acid, and sodium fluoride, which would be its weak acid conjugate base. Our good friend, like you're going to use today, acetic acid and sodium acetate, which is a weak acid conjugate base. And the favorite choice of any buffer example is acetic acid and sodium acetate. But you can also do like a weak base, like ammonia and ammonium chloride, for example. That would be a weak base and its conjugate acid. So for example, we'll choose the non-used one a lot. We'll go with this one. So if I made a buffer out of those two things, it is really here HF and F minus that is really the buffer part. This is the acid part, and that is the base part. The sodium is really just a spectator ion. It's just there to kind of balance out the charge. It's really not doing anything. And that's why it's referred to as the salt of its conjugate base, because it has a sodium basically there. But the real two things that are really the active part of the buffer in this case is the hydrofluoric acid and the F minus or the fluoride. And that's because when I put that into solution, because it's a weak electrolyte, and I dump that hydrofluoric acid in, it is going to set up an equilibrium, if you remember, with those arrows heading in both directions, and it's going to make H plus and F minus. You help this out by putting a little extra F minus in there to get the concentrations really good. But basically, both of those guys are in solution together. And what you have in a case like this, when you have a buffer that is made up of these two things, is you now have a acid part of the buffer, which would be the HF, and you have a base part of the buffer, which is the F minus in this particular example. And that is really critical for how a buffer works, is having both of those things in solution to begin with. So unlike a strong acid or strong base where you can't get them both in there, you can only get like an acid part or a base part. With a weak acid or weak base, you're able to keep in solution both the acid and the base together, floating around in that solution. And that's really critical for how it works. So let's see how it really does work here. Let's start with a non-buffer solution. Also, what you're going to use today, which is everybody's favorite water, is a non-buffer. If I take my strong acid, like hydrochloric acid, and I add it to water, it will, as we've been talking about, break apart into H plus and Cl minus, which means my beaker over here, as I drew a second ago, will have a lot of H plus and it will have some Cl minus. And what affects the pH is minus the log of the H plus concentration, right? So in this case, I just dumped this into water. I generated a lot of H plus. The concentration of H plus goes up. Concentration of OH minus goes down. And now because we have a lot of H plus in there really quick, the pH drops a lot, right? Because that's basically what will make the pH change a lot. You will see a pretty big jump down in pH because we made a lot of free H plus by adding that acid to the water. So in this case, for example, if our water started at like a pH of 6, it will drop maybe all the way down to like a pH of 1 because there's just so much H plus that has been added to that water really quickly that makes a really big jump in pH. Now, if we added sodium hydroxide, a strong base, to water, a similar thing will happen here. We will make sodium ion and hydroxide ion. And once again, 100% of what we have in that solution are the ions, right? We have none of those guys together. So if we draw a little picture, we got a lot of sodium ions, but more importantly, we have a lot of hydroxide ions that have now been freely floating around in the solution. So once again, as the hydroxide concentration increases, the H plus concentration will decrease. And what we will see is the pH will actually jump up higher because there's a lot more OH minus in the solution in this case. We will see a pretty big jump in the pH because we made a lot of free OH minus in this case. So we would see the pH, for example, if it started at 6, jump up to maybe a pH of 13, a really big jump in the pH. And that is because water has nothing in it to be able to handle any of the incoming H plus or the incoming OH minus. So it just lets them go and float around freely. And because they're floating around freely, that increases their concentrations and has a really drastic effect on the pH as to why it jumps up high or up low. Questions on that so far? So let's see so if we take these exact two acids and bases and add it to a buffer, and we'll use our buffer here of hydrofluoric acid and sodium fluoride. So now that we have in this beaker, we have the HF floating around. We have our H plus that's there to start with, and we have our F minus floating around. So once again, we have the acid part of the buffer and we have the base part of the buffer actually in the solution to begin with. So now when we take to our buffer here, we take our hydrochloric acid and I go and dump this guy into here. When the hydrochloric acid, which is an acid, will it react with the acid part of the buffer or the base part of the buffer? The reactions are called acid-base reactions. So when you dump in the HCl, it's going to go and find the base. And those two guys are actually going to do a reaction. So what's going to happen is the HCl and the sodium fluoride in this example will react. It's a double displacement reaction, right? They switch partners. And we will make HF and we will make sodium chloride. Now, if we look at what we made, this always happens when you have a buffer. We added some acid and we actually made HF, which was part of the buffer to begin with. So you actually make part of the buffer as you are reacting it with an acid or base. We make sodium chloride, which is a neutral salt. You don't have to worry about that. So that's not going to affect the pH. So really in this case, by adding this to the buffer, we made part of the buffer, we used up some of the buffer, but it's actually what we do not see here that's really important. We do not see what here that we do see here. When we added the HCl to water, we made a bunch of H plus, free H plus. When we added the HCl to our buffer, because of that reaction, all the H plus got tied up right there. So we did not produce any free H plus. So we do not see any free H plus being formed. And because the concentration of H plus then remains relatively constant, that would also mean that our pH will remain relatively constant as well, because we did not add any more H plus really than was there to begin with. There was some to begin with right there, right, when we started, but we didn't add a bunch of it to it. I say relatively constant because in reality, we are going to add a little bit because we're making a little bit of HF, so that'll make a little bit more H plus. So you will see the pH come down a little bit, but you will not see the tremendous jump in pH as you would see in water, because we didn't create a ton of H plus really quickly like we did in water. Any questions on that there? So let's take a look at what happens when we do the base. So in the same situation here, we're going to add the base to this buffer. So once again, in our solution, we have our equilibrium that's been set up with our H plus and our F minus. Again, the acid part of the buffer and the base part of the buffer in there. We're now going to add some sodium hydroxide into here. When I add that sodium hydroxide in, it will react with which part of the buffer? Should react with the acid part. So when you dump that base in there, it will then go and react with the acid. And what you're going to get is actually an acid-base reaction here. And when you have an acid-base reaction, it's still a double displacement. You get water and a salt, which is sodium fluoride in this case. These guys basically switch partners. The result of that is you made water, which will not affect the pH. You also made more of the buffer that was there to start with, which will not affect the pH. But it's the same really answer here. What we do not see that we saw with water is when we added the base to water, we made a ton of OH minus. In this case, when we added that base to our buffer, we made basically water. The OH minus got tied up there in water. So what we do not see here is we do not see a lot of free OH minus. And what that means is the concentration of OH minus is relatively constant, which means because H plus is tied to that, the H plus concentration will stay relatively constant. And that means that the pH will also stay relatively constant as well, because there's really no net change in the amount of H plus in that solution. So how a buffer works is because it has an acid part and because it has a base part, and they're both in the solution together, when you add additional acid or additional base into that buffer, it's able to tie up the free H plus and the free OH minus into either water or basically the acid, and that prevents the formation of free H plus or free OH minus. And what that all does is keep the H plus concentration relatively constant, and the pH stays pretty much constant as well. You don't see a really big jump in the pH. Any questions on that there? So just to visually end on here, if you were to make a buffer, you typically have an acid part and a base part. And a lot of times you'll start with about equal amounts of both of those. When you add acid to that buffer, it will use up some of the base, but it will make some of the acid part of the buffer. And that's why a buffer can maintain a pH over a long period of time, because you're kind of regenerating part of the buffer every time you do the reaction. So it's able to kind of keep itself there for a while. If you add some base to the buffer, it will react with the acid part and you'll make some more of the base part of the buffer. And in our example there, the acid part of the buffer is the HF, the F minus in this particular case. But there is a limit to buffer, and it's sometimes referred to as buffer capacity, which means if I were not to read the instructions, which I'm sure would never happen, but you just keep adding acid, what's going to eventually happen here? If you just keep adding acid, you will continue to use up the base part of the buffer, right? Until frankly, there is no buffer left, base part left, which means as you continue to add acid at that point, you're going to be adding a bunch of H plus to the solution. And at that point, you would see a really big jump in pH. That's why it's really important when you make a buffer that the concentration of the buffer is appropriate for the concentration of the acid that you grab. So for example, if you grab the 18 molar off the shelf and dumped it into your solution, way too much acid, your buffer would not be able to handle it. You'll blow right through it. So there is a limit to how well a buffer could work. But the ultimate goal is a buffer is able to prevent really the formation of free H plus or free OH minus. And all that does is keep basically the H plus concentration constant, and that keeps the pH relatively constant. Any questions on that there?